Hello everyone, welcome to this session on Introduction to Power System or Transient Stability. In this session, we will understand what is power system stability and its classification. So let's first understand what is power system stability. So power system stability is the ability of an electrical power system for a given initial operating condition to regain a state of operating equilibrium after being subjected to a physical disturbance, with most of the system variables bounded so that practically the entire electrical system remains intact. These disturbances can be defined as various type of faults such as three-phase, line to ground, line to line, etc. Change in load such as load addition and load rejection. Then loss of generation such as generator outage or power grid outage. Starting a motor that is large relative to a system generating capacity. Impact loading on the motors, which means gradual increase or gradual reduction in the motor load. Transmission line outages, voltage collapse, and so on. So here we will understand power system stability classification. So as you can observe here, power system stability can be classified into rotor angle stability, frequency stability, and voltage stability. And all of these three stabilities can be further classified into large disturbance or small disturbance, short term or long term. So you can observe here the rotor angle stability can be classified as small disturbance rotor angle stability and large disturbance rotor angle stability, which is also called transient stability. So this rotor angle stability is short term stability, whereas frequency stability and voltage stability can be either short term or long term stability. First we will understand rotor angle stability. So the rotor angle stability is the ability of the electrical system to remain in synchronism when subjected to a disturbance. The rotor angle of a generator depends on the balance between the electromagnetic torque due to the generator electrical power output and the mechanical torque due to the input mechanical power through a prime mover. Now, due to some disturbances in the electrical system, if the balance between electromagnetic and mechanical torque is disturbed in the generator, then this will lead to oscillations in the rotor angle. As mentioned in the previous slide, rotor angle stability can be classified into small disturbance rotor angle stability and large disturbance rotor angle stability. So let's first understand small disturbance rotor angle stability. It is the ability of the system to remain in synchronism when subjected to a small disturbance. If a disturbance is small enough so that the nonlinear power system can be approximated by a linear system, then the study of rotor angle stability of that particular system is called small disturbance rotor angle stability analysis. These small disturbance can be small load changes like switching on or switching off small loads, line tripping, small generator tripping, etc. Due to these small disturbances, there can be two types of instability: non-oscillatory instability and oscillatory instability. In non-oscillatory instability, the rotor angle of a generator keeps on increasing due to a small disturbance, and in case of oscillatory instability, the rotor angle oscillates with increasing magnitude. Now let's understand large disturbance rotor angle stability. It is the ability of the system to remain in synchronism when subjected to large disturbances. These large disturbances can be fault, switching on or switching off large loads, large generator tripping, etc. When a power system is subjected to a large disturbance, it will lead to large excursions of the generator rotor angle. Since there are large rotor angle changes, the power system cannot be approximated by linear representation. like in the case of small disturbance stability. The time domain of interest in case of large disturbance as well as small disturbance angle stability is anywhere between 0.1 second to 10 second, and due to this reason both small disturbance and large disturbance rotor angle stability are considered as short-term events. Now let's understand frequency stability. So it is the ability of a power system to maintain steady state frequency following a severe disturbance between the generation and the load. It depends on the ability to restore equilibrium condition between system generation and load with minimum loss of load. Frequency instability may lead to sustained frequency swings which may cause the tripping of generating units or the loads. So during these frequency excursions, the characteristic times of the processes and devices that are activated will range from fraction of seconds like under frequency control to several minutes corresponding to the response of devices such as prime mover, and hence the frequency stability may be a short-term event or a long-term event. Though the stability is classified into rotor angle, voltage and frequency stability, they need not be independent isolated events. A voltage collapse at the bus can lead to large excursions in the rotor angle and frequency. Similarly, large frequency deviations can lead to large variation in voltage magnitude. Each component of the power system, that is prime mover, generator rotor, generator stator, transformers, transmission lines, load, controlling devices, and protection systems should be mathematically represented to assess the rotor angle, voltage, and frequency stability through appropriate analysis tools. Now in this slide, we will understand voltage stability. So the voltage stability is the ability of the electrical system to maintain the steady state voltages at all the system buses when subjected to a disturbance. So if the disturbance is large, then it is called as large disturbance voltage stability, and if the disturbance is small, it is called as small disturbance voltage stability. Unlike rotor angle stability, which was short-term phenomenon, the voltage stability can be short-term or long-term phenomenon. In case voltage fluctuations occur due to fast-acting devices like induction motors, power electronics drive, HVDC, etc., then the time frame for understanding the stability is in the range of 10 to 20 seconds, and hence voltage stability can be treated as short-term phenomenon. On the other hand, if voltage variations are due to slow change in load, overloading of lines, generators hitting reactive power limits, tap changing transformers, etc., then the time frame for voltage stability can stretch from 1 minute to several minutes. Here the main difference between voltage stability and the rotor angle stability is that the voltage stability depends on the balance of reactive power demand and generation in the system, whereas the rotor angle stability mainly depends on the balance between real power generation and the load demand. This will end our session here. Hope you have found this session useful and informative. Thank you.